Listen to part of a discussion in a general science class.
Okay, this is a general science course, and as such, the first thing I want you to understand is the scientific method. In your book, the definition of the scientific method is an organized approach to explaining observed facts with a model of nature that must be tested and then modified or discarded if it fails to pass the tests. So, let's take that apart and talk about it. What are observed facts? Anyone?
I'll try.
Okay.
Isn't a fact supposed to be a statement that everyone agrees on?
So you'd say that a fact is objectively true.
Yeah, that's what I mean.
Okay, that sounds good. But what about this? We consider it a fact that the sun rises each morning and the earth rotates. But facts like that aren't always agreed upon. Look, when we say that the sun rises each morning, we assume that that's the same sun day after day, an idea that might not have been accepted by ancient Egyptians, whose mythology taught them that the sun died with every sunset and was reborn with every sunrise. Now, let's consider the case of the Earth's rotation. Well, for most of human history, the Earth was assumed to be stationary at the center of the universe. So, as you can see, our interpretations of facts often are based on beliefs about the world that others might not share. Still, facts are the raw material that scientific models seek to explain, so it's important that scientists agree on the facts. How can we do that?
How about this? A fact has to be verified. I mean, that's where the testing comes in. So we have to be able to test a model, but we have to be able to test a fact too, right?
Now you're on the right track. In the context of science, a fact must therefore be something that anyone can verify for himself or herself, at least in principle. So, even though the interpretation may be different, some interpretation of the sun is there every morning, and that can be verified. Then a model's proposed to explain the facts. And a model is?
An explanation of the facts.
Right. Once the facts have been observed, a model can be proposed to explain them and not only explain what's obvious, but also make predictions that can be tested through further observations or experiments. Let's go back to Ptolemy's model of the universe, which assumed that the Earth was the center of everything. Okay, that was a useful model because it predicted future locations of the sun, moon, and planets in the sky. However, although the Ptolemaic model remained in use for nearly 1,500 years, eventually it became clear that its predictions didn't quite match actual observations, a key reason why the Earth-centered model of the universe finally was discarded.
So models are discarded when they don't match the observations.
Exactly, and new models are proposed to explain the facts in a better or more inclusive way. Okay, how does a model achieve the status of a theory?
Well, I guess sometimes the model doesn't fail. It gets repeated by many experiments and the predictions are verified.
So when a prediction's verified, repeated, then we start to assume that the model's a valid representation of nature. And when that happens, with many experiments and a number of different researchers, then the model achieves the status of a scientific theory.
But...
Yes, Jerry?
Well, the problem is that theories get discarded too, don't they?
Absolutely, because it isn't really possible to prove that a theory is true beyond all shadow of a doubt. And that's good because doubt is a cornerstone of science. Even a well-researched and presented theory should undergo continuous challenges from the scientific community with further observations and experiments.
I'm sorry, did we mention the term hypothesis? Does that fit in with a model or a theory?
Glad you brought that up. A proposed model is often called a hypothesis, and that just means that the scientist is making an educated guess that the model's predictions will bear up under testing.
So a hypothesis is a proposed model.
Right. But let's put this all together, shall we? Step 1's observation, the collection of data, that is, observations. Step 2's hypothesis, or a model to explain the facts and to make predictions. Step 3's additional observations and experiments. And here's the important part. When the predictions fail, then we recognize that the model's flawed, and we have to revise or discard it. But when the predictions are verified on a consistent basis, then we consider the possibility that we have a true representation of nature, and we elevate the model to the status of a theory.
So step 4 is the theory?
Right. But even then, the theory must undergo step 5. That's further observations, experiments, and challenges. Okay so far? Okay. Now for a reality check. In the real world of science, discoveries are rarely made by a process as mechanical as the idealized scientific method outlined in your textbook, the one that we just summarized. For example, anyone recognize the name Johannes Kepler?
Sure, didn't he propose the laws of planetary motion?
He did, in about 1600. But instead of verifying new predictions on the basis of his model, he tested the model against observations that had been made previously. And like most scientific discoveries, Kepler's work involved intuition, collaboration with others, moments of insight, and luck. And eventually, other scientists made a lot of observations to verify the planetary positions predicted by his model.
Then, go ahead.
So the scientific method in the book, that's not really the way it happens a lot of the time?
Okay, let's put it this way. The scientific method's a process that we need to keep in mind as we do the work of scientists. But we should also understand that it's an idealized process for making objective judgments about whether a proposed model of nature's close to the truth. And we should also keep in mind that in the work of scientists, other factors are also brought to bear on those ideal steps in the process.